Okay. So today we're going to answer this question finally. We talked about it last time, and we sort of saw what we needed to do. Again, the key idea in solving the problem is to introduce a better parameter space for conics. This is a problem involving the condition of tangency. And the problem with the naive space of conics, just the P5, is that it doesn't keep track of tangent lines. In other words, if I write down a double line, it appears that every line in the plane is tangent to it, and every conic is tangent to it, and so on. And that means that if I take the condition of being tangent to a conic, and I take the corresponding cycle, the subvariety of P5, then those cycles will not intersect transversely. They'll all contain the locus of double lines. So that was the preamble. And then last time I suggested what was classically the solution to this problem. And that is to introduce a new notion of conic. This is called a complete conic. So what we do is we'll let P5 be the space of conics in P2 as usual. And we'll also introduce the space P5 dual, which is the space of conics in P2 dual. And I'll repeat one thing I said last time. These projective spaces are, in fact, naturally dual to one another, but that's not relevant. The only reason I'm putting this asterisk here is so that I can distinguish the two P5s. Okay? So just take this as the definition of P5 and P5 dual. What we're going to do is we're going to look at the locus of pairs of dual conics, pairs of dual smooth conics. And we're going to take the closure of that locus in P5 cross P5 star. So this is closure of the locus of pairs C, C star, such that C and C star are dual smooth conics. And the claim is that this space will exactly do what we want. Okay, so but before we get into that, let's just talk a little bit about what this space looks like, what sort of points are in it. And it's just such a beautiful space, it's worth taking the time in any case. Something else I said, I think it was back on Monday, seems like a long time ago, but I'll repeat it now, is that, enumerative geometry and intersection theory in general, it's not about the numbers. It's really about our understanding of the geometry of the objects involved. And when we see a space like this, it's worth taking the time to try to understand what this looks like. If we really want to understand conics and tangencies, and plane curves in general, and conditions of tangency, we really want to look and see what this space looks like. So let's draw a picture. And it's sitting inside a 10-dimensional complex manifold, so the picture is going to be a little inadequate. In fact, instead of trying to draw the product of P5 cross P5 dual, let's just, I'll do something almost as difficult. I'll draw a picture of P5. And this is P5. It looks like P3, but it's bigger. Okay, this is how you tell the difference. And again, I think of this as the space of conics in the plane. Now, the point is there are three kinds of conics in the plane. There's smooth conics, and they form, obviously, an open subset, this P5. Then there's a space of singular conics. This is typically called the discriminant hypersurface. And I'll denote that. Of course, again, it's fourfold, but I'll denote it by a surface, or anyway, delta, we'll call that. And that's the locus of singular conics. And of course, a general point here is, a general point in this space corresponds to a conic, which is the union of two distinct lines. Okay? And that's, so I'll write that as L plus M. And the intersection I'll call P, a point P. Maybe I should draw a picture of that. this is now L2, which is, you see, smaller. So L, and then there's the point P. I'll probably redraw this in a moment because we're going to be working with the picture in the plane and in P5 simultaneously. There's one more locus, of course. There's a further specialization. We can have the singular conic, which generically, again, consists of a sum of two lines, specialized to a double line. And this, as we saw, we called S. It's, as a subvariety of P5, it's the Veronese surface. But again, that's not going to matter to us so much right now. The main point is that a general point here corresponds to a curve which is just the double of a line L. So that's our picture of P5. And now the question I want to ask is, what points in this subvariety of the product in phi lie over each type of these points? So we're going to ask, in effect, well, I can phrase the question either one of two ways. I could say, as I just said a moment ago, what are the fibers of phi over each type of point? Phi is very nearly a homogeneous space. I mean, the automorphism group of the plane acts on the space P5, it acts on P5 dual, and it acts on phi as well. And so there really only are, as we'll see in a moment, 4 orbits. In any case, the point is that the fiber over a point in P5 should depend only on which of these strata it's in. So we have essentially 3 questions to ask. What are the fibers over each of these types of points? Okay? And again, and one of them, by the way, one of those 3 questions is trivial. If I have a smooth conic, there's no ambiguity, right? I mean, if I have a smooth conic, a point out here outside of delta, then of course there's only its dual corresponding to the unique point in phi lying over that. So the map from phi to P5 by a projection on the first factor is certainly an isomorphism away from delta. That's easy, or at least should be clear by the definition. Now we ask, what are the fibers over other types of points? And another way of saying that is, if we have an arc or a one-parameter family, and you can think of this depending on whether you're sort of complex analytically minded or algebraically as either, just think of it as an arc. If this is an arc in P5, okay, specializing to a singular conic, say C0. So I'm going to assume that CT is smooth for T not equal to 0. And I want to also assume that it specializes to something singular. So I'm drawing an arc in P5 that is generically outside of delta, but specializes to a point like that. Okay? And the question is, what is the possible limits, or I should say, what are the possible limits of the dual conic? So again, for T non-zero, I can look at the set of tangent lines to the smooth curve CT. That itself is a curve in the plane, a conic curve in the dual projective plane. And I can ask, what's the limit of that dual curve as CT approaches the singular curve? So let's start with the example of a degenerating family of conics that you have seen now several times this week. I think Robin was the first to introduce this. He said, you know, if we look at the space of conics, we can have a family of conics that are generically smooth for T not equal to 0, specializing to a union of 2 lines. And the standard example is xy minus t. So that's just a family of hyperbolas with vertical and horizontal asymptotes. And it approaches the pair of the coordinate axes. So the question is, okay,
Each of these smooth conics for t non-zero has a dual conic. What's the limit of those dual conics? So I'm asking, if I take a family of lines, LT, let's say, where LT is tangent to CT, so this is the equation of CT, and I take the limit as t goes to 0, what can you tell me about that limiting line? What lines are limits of tangent lines to these curves? Well, there's a couple obvious ones. Yeah. You know? I mean, clearly the horizontal and the vertical. And, you know, in fact, if I look at the collection of points, say, look at the point, let's see, 1 comma t. So I'm just looking at the points on these curves, and I look at the tangent lines at those points, they're approaching the horizontal line, and likewise over here. What other lines are limits of tangent lines? There have to be more. By upper semi-continuity of dimension, if you want to give it a fancy name, the limit of the dual conic CT star has to be a curve in P2 dual. And so it can't just consist of 2 points. What other lines in the plane are limits of tangent lines? Yeah, exactly. That's the point is, if I look at a family of points approaching the point P, remember that was our letter for the intersection of the 2 lines in our singular conic. If I have a family of points approaching that point P, for example, if I look at the points square root of t, square root of t, it's still an arc, it's 2 to 1 over its image, but okay. Then, of course, the tangent lines at those points approach the line through P with slope -1. And in fact, if I take other families of points approaching the node P, I can get any line through the origin as a limiting tangent. So here, if I took, for example, this family, I would just get a family of lines specialized to a line of larger slope, or more negative slope, I guess I would say. So what's the conclusion? Let's write this down. So the first thing we see is that if C0 is specifically a conic consisting of 2 distinct lines meeting at a point P, then the limit of CT dual, the limit of the dual curves, can only be the family of lines through the origin. No other line can be a limit of tangent lines. So, well, I'm going to write that by saying that the limit of the dual conics is the double line in P2 dual, which I'll denote P star. So P star is the line in P2 dual to a point P in P2, or if you want to think of it this way, it's just a set of lines through P. Okay, it's a line in P2 dual. I apologize, but this is, even if this notation is not ideal, it's the best I can come up with. So the point is that the limit of the dual conics is a double line in the dual projective plane. And this is the key point. It's unambiguous. It does not depend on the family I chose. It does not depend on the arc CT. It depends only on the limiting point. If I tell you I have any family specializing to this curve C0, then the limit of the duals has to be this double line. So this, again, depends only on C0. And what that means in turn, if I think of the phi here as mapping to P5, what I'm saying is the fiber over a point in delta away from this surface S of double lines, the fiber over a point like this is just 1 point. So I said before that the projection map from phi to P5 is an isomorphism away from delta. In fact, it's an isomorphism away from S. Let me write that down. In fact, the projection map from phi to P5 is an isomorphism away from the surface S of double lines. All right. So now it's time to ask the remaining question, which is, what happens if I have a family of conics specializing in a double line? Let's draw a couple families and see what it looks like. Start with a fairly simple one. I mean, you can take pretty much any conic and just mash it down to a double line by simply multiplying one of the coordinates in the plane by t. In fact, let me write down exactly such a family of conics. So I could take something like y squared equals t times x squared minus 1. So what does that look like? Well, for time t equals 1, it's a standard hyperbola with asymptotes at 45 degrees. And as t goes to 0, we're simply flattening it. All we're doing is multiplying the y coordinate by the square root of t. But the point is we're just sort of shrinking the distances in the vertical direction. So we get a family of hyperbolas that look like this. It has sort of asymptotes of lower and lower slope. And of course the limit as t goes to 0 is simply the double. Let's see if I can do this. Nope. Okay. I just have to draw it forcefully. The double line. Okay. So this again, we're looking, I want to think about this in general. What is so this is a family of generically smooth conics specializing to a conic which is just a double line. And again, this will be the line L. And again, we ask, what is the limit of the dual conics? So what lines in the plane, in other words, are limits of tangent lines to these hyperbolas? And again, there's one obvious one, which is the horizontal line. But again, just as before, there have to be others. Well, I mean, in fact, if you look at this picture as it happens, you can see a couple others. If you just look at the vertical line through the point x equals 1, through the point, vertical line x equals 1, that actually is tangent to CT for every t. So that's a point in common of all the dual conics, and so in particular, it's certainly a point in the limit. So now we have 3 lines that are limits. What else? I mean, you were gesturing, so I thought you wanted to.
Double line.
Pardon me?
The line on the other side.
Yes. So we have this vertical line as well. Again, that's tangent to all the members of the family, and so in particular it appears in the limiting curve. What else? Well, you know, think about what we did over here. The point is, if we look at a family of points on these curves CT, in this example, if those points tend to any point other than P, then the limiting tangent line, there's no choice. It has to be either the vertical line or the horizontal line, depending on the limit of those points. Likewise, if I have a family of points here specializing to a point of L other than these two, then the tangent line necessarily is horizontal. So what we have to do is look at families of points on these conics specializing to one of these 2 special points. Let's give these guys names, in fact. We have P, let's call this one P and call this Q. And now we see that, in fact, we can get every line through those points as a limit of tangent lines. If I have a line like this, I probably shouldn't try to draw this on the board, at least not with all the stuff that's going on already, but I'll do it anyway. If I have any line through one of these points, I can realize that as a limit of tangent lines to the nearby conics. Okay?
So in other words, saying that, I mean, if you consider lines as slope 1, for any one of those conics, there's going to be one of those tangents.
Exactly. That's a very good way to put it. Robin points out that if I draw lines parallel to this one, then every one of the conics CT will have, for example, if this is the line with slope 1, every one of the conics CT will have a line with that slope, a tangent line with that slope, and those tangent lines will be tending to the line through P with that slope. So the conclusion is that the answer to this question is that the limit, as t goes to 0, of the locus of tangent lines, of the dual conics, in other words, is just the set of lines through P union the set of lines through Q. It's, in fact, it's in the dual plane, it's a union of two lines. So there are many things that are beautiful about this. One is the sort of this phenomenon that you get used to in birational geometry, but it's always a little bit confusing, at least to me, that if we have, so to speak, a generic degeneration of a conic to the simplest kind of singular conic, the dual is necessarily becomes, where did I write that, and where is it gone? Yeah, the dual becomes a maximally degenerate conic, double line. If I have a family of conics, or at least this particular family of conics, specializing to a double line, the dual specializes to a line pair. Yeah?
When you first posed it, that's a very convenient picture, because you see the 2 points.
Yes, yes.
The first picture I thought of, what he said, was to take a horizontal line and take a circle.
Right.
And then stretch it out and flatten it at the same time. So you
Simultaneous.
get thinner ellipses like
Yes.
big balloons.
That's right. But now you show your 2 points. The points analogous to these two in that picture are tending to infinity.
Yeah, so if you get the 1 point,
Right.
infinity.
No, exactly, exactly. And I actually was going to draw an analogous picture
What's
here.
the dual in that case?
Well, I'll show you in a moment, okay? But I was going to use a slightly different picture because I want to see. So Robin's suggestion was, let's look at another family. Let's look at a family that we get by starting with a circle and simultaneously collapsing the y-axis and expanding the x-axis. We apply, in other words, the automorphism 1 over t, 0, 0, t in the plane. This linear transformation in the plane, and we get a family of ellipses, which I won't be able to draw, which get flatter and flatter and approach the double line. And that's exactly analogous to the next example I was going to do, but you'll see in just a moment. Let me do this now, in fact. What I was going to suggest was, by analogy with what we had there, we could have a family of hyperbolas specializing to the double line y equals 0, but where the 2 points P and Q, as Robin wants, approach each other. Yeah?
Yeah, another comment you can make is that it would be a nice exercise to compute this and see
Yes.
how the t goes to the other side. And,
Exactly. I thank you for pointing that out. If you're at all interested in it, it's a wonderful just exercise to take the pictures I'm drawing and calculate the dual conic. It's not a hard thing. If I give you a quadratic polynomial in the plane, a quadratic polynomial, say homogeneous in 3 variables, to write down the equation of the dual conic. You just take that quadratic equation, that quadratic polynomial, you restrict to a general line, and you set the discriminant equal to 0. And that's an equation on the coefficients of that equation of that general line. That's the equation of your dual conic. You can write this down explicitly, and you can see algebraically the truth of what I'm saying. So I really urge you, if you have any interest at all in pursuing this, just to sort of do that exercise, and do the same for all the families that I'm going to write down. The next family I wanted to write down was sort of similar to this, but I'm just going to make it tx squared minus t squared. I think that's the one I want. The point is, what's happening here is that the points, the relevant points P and Q, which in this picture are the points minus 1, 0 and 1, 0, they're now moving. They are both approaching the origin. And the picture is, again, we start for t equals 1 with the hyperbola, the same hyperbola. But now, as we contract the y-axis, we're simultaneously pulling the x-axis in. So we're going to get a family that looks like this. And of course, again, the limit is, because these things are simultaneously flattening as these 2 points approach each other, the limit is again the double line. Again, if I set t equal to 0, all I get is y, y squared equals 0. And the point is, in this case, the limit, if I have this point P, the limit of the curves CT, or rather of the dual curves, is just the locus of lines through the point P alone doubled. Okay? So, in fact, what we can see, and what you can see if you write down the equations, is that when I have a family in general, if CT approaches a double line L, right, then the limit of the dual conics, CT dual, is necessarily a conic in the dual projector plane of the form P star plus Q star for some pair of points P, Q, and L. This, by the way, is a good time to explain, or not maybe to point out, this is why I'm using divisor notation. When I write a conic, like for example this one, a line pair, as L plus M rather than L union M, I want to use divisor theoretic notation because that allows me to handle the various cases more uniformly. So in this case, if the conic approaches a double line, the dual conic approaches a sum of 2 lines corresponding, or dual to, points on that limiting line, L, which may or may not coincide. In this case, they coincide. In that case, they don't. But they could be a priori any points. So this is, I mean, in some sense, answers the final question, but it's worth pointing out. The contrast here is, in the previous case, where the family of conics approached a line pair, the limit did not depend on the family. It depended only on the special limiting curve. In this case, the limit does depend on the family, and not just on C naught. Again, that is the crucial point here, and it's illustrated right here, for example, with these 2 families. These 2 families both have as limits the double of the horizontal line through the origin, but the limit of the duals is different in the 2 cases. And in fact, what we see is that we have many different possible limits for the duals. In fact, they correspond exactly to divisors of degree 2 on the line L. So let me write that down here. The fiber of phi, so what we've just seen is that the fiber of phi over a point of the form L plus n, where L is not equal to n, is unique. It's a single point. And the fiber of phi over a point C is equal to 2L over a double line consists of, or corresponds to, the set of divisors, effective divisors of degree 2 on L. And, of course, a pair of points on a line is simply the 0 locus of a quadratic polynomial, unique up to scalars. So this is isomorphic to P2. So the picture here is, when we look at phi mapping down to P5, it's an isomorphism away from S, away from the locus of double lines, and over S, it's a P2 bundle. Now, somebody already raised this point, but this is a good time to recall it. This looks an awful lot like the blow-up of P5 along the surface. I mean, think about it. blow up P5 along a smooth surface, this is exactly what you expect to see. An isomorphism away from the surface, and over the surface, a P2 bump. And this is, in fact, the blow up. The point is, you know, this is where blow-ups come from. When people define blow-ups, they did so because they had seen them over and over again. It was a pattern, a typical thing that arose in these kind of geometric constructions. And they were trying to sort of say, well, look, this is something we can do in general, and here's how we would define it in general rather than ad hoc. But in some sense, the way to understand blow-ups, at least in one view of the world, is to start by looking at examples of naturally occurring blow-ups like this, and then you can appreciate, ultimately, the definition of a blow-up in general in these terms, to understand this. Okay, let's see where we are with time, and then we'll move along. All right, good. So before we move, any questions about this notion of complete conics? Yes?
Yeah, because I'm noticing that all this discussion you do in P5, you could have done at the same time in P5 star.
Yes.
You're blowing up S star.
Yes.
You're blowing up S in the phi in one direction and blowing it down a different
That's
direction.
right.
Isn't that what's called a flip or a flop or something?
No, because I'll explain why in just a moment. This is not a flip or a flop, either one. Because basically, yeah, so let me explain another point of view on this, and Robin makes an excellent point. This situation, this whole picture, even though I've chosen to focus on the projection to P5, it's completely symmetric. It comes down to the fact that the dual of a conic is the original conic. So I could have looked at the projection to P5 star and described it exactly in the same way as the blow-up of P5 star along the locus of double lines in that plane, in P2 star. It's not a flip because when so phi is simultaneously, what we're saying, the blow-up of P5 along the Veronese surface of double lines in P2. We can also realize it as the blow-up along the locus of double lines in P2 dual of the space of conics in P2. But the point is, when you realize it by a projection on the two factors, the exceptional divisors are different subvarieties. In a flip, what you do is you blow something up, and then you blow down the same exceptional divisor via a different map. So that a flip is necessarily, for example, a birational isomorphism that is actually biregular outside of a locus of codimension 2 in both sides.
So the exceptional...
So in fact, let me write down, the next thing I was going to write down should at least allow me to answer that more concretely, okay? And it's useful to know because we're going to need to know a class, sort of a description of all the points in phi star, or in phi, excuse me. So the conclusion is, again, phi is that we think of as the set of complete conics. So this is the definition of the term complete conic. It's a point in phi. And there are 4 types of complete conics, each of which corresponds to a locally closed subset of phi. First of all, there's type 1, which is simply C star, where these are both smooth and dual to one another. And again, this is just, as we saw, isomorphic to the subset of smooth conics in P, it's isomorphic to the open subset of P5, which is just the set of smooth conics. There's type 2, which was this first degeneration we looked at, which consists of a conic of the form L plus n, where L and M are distinct, and the dual conic is necessarily 2P star, where P is simply the intersection of L and M. Then, there's, in some sense, dual to this, there's pairs consisting of 2L and P star plus Q star, where P and Q are in L, and in fact are distinct. So I can write that by saying L is the line spanned by P and Q. That's the example we saw first of a degeneration to a double conic, and a double line, excuse me. And finally, type 4 is sort of the most degenerate. It consists of double lines in both planes, 2L and 2P star, where again P has to lie in L. So Robin, these are each locally closed subsets, and their closures, well, the closure, this is open and dense, so closure is everything. The closure of these two are divisors. They're dimension 4. And this is, you can check, well, clearly from the condition, dimension 3. The point is, if I project onto P5, that expresses phi as a blow-up of P5 along the Veronese surface with 3 as the exceptional divisor. If I project the other way, I'm expressing it as a blow-up of P5 dual with 2 as the exceptional divisor. So you're right. Phi is the graph of a birational map from P5 to P5 dual. But it's not a flip because it's not regular outside of codimension 2 on both sides. Okay. So these are the 4 types of complete conics. And again, you can think of this as, in some sense, as a stratification of phi. And again, one last thing. Remember that this open subset is just the original set of smooth conics. What this is, and this is, in some sense, the way to think of this is as an alternative compactification of the space of smooth conics. Are there any questions about this? Now we have to see that it does what we want. The key feature of this, I mean, the problem we were trying to address is that when we look in the naive space of conics, P5, and we look at the conics tangent to a given conic, I take the closure, those cycles fail to meet properly. Have we fixed the problem, is the question. Let's do that. So the first thing to check, in some sense, is exactly this. Because if this doesn't work, then there's no point in going ahead with the sort of intersection theoretic calculation. The thing is this, okay, so let's let D in P2 be a smooth conic. And now, but I want to do exactly what I did in P5. I want to take the set of conics tangent to D. I want to start with the conics where I know what I mean by that, right? I want to take the set of smooth conics tangent to D. And I want to take necessarily the closure of that locus, but now not in P5. I want to take the closure in phi. So I'm going to let Z sub D be the closure of this in phi. Okay? And again, the problem was if I did this in P5, then if I took 5 such cycles, they would not meet properly. So the first thing to check is, and I'll write this as a claim, which will now justify, that if C1 up to C5 are general conics in the plane, in particular smooth, then the intersection of these corresponding subvarieties, Z sub Ci, is entirely contained in the locus of smooth conics. In other words, there's no points of intersection of these corresponding to degenerate conics. And that again, if you think of this as a blow-up, right, it's at least plausible. We can be hopeful that this is the case, because this is what happens when we blow something up and take proper transforms. That's exactly what we're doing here. We're blowing up the locus of double lines and taking the proper transform of the cycles we had in P5. And it's not unreasonable to hope that we might actually have separated them, at least over the locus of double lines, where they met improperly before. Sorry there. So is the question well posed, or at least unambiguous? Let's do it. And now here I'm going to have to again just appeal to your geometric intuition. But again, I will say, or as was pointed out, you can write these things down. You can do this all in coordinates. And in some ways, you should. You shouldn't just take my word for it that these things would work out the way I say. So to prove this claim, we have to first ask a question, or rather answer a question, or rather both. We have to ask, which conics, complete conics, of types 2, 3, and 4 lie in ZD? So here I have a conic. Call it D. I look at the locus of smooth conics tangent to D. And I want to take the closure of that in phi. Again, I know what I mean by saying that a smooth conic is tangent to D, but what do I mean when I say that a degenerate conic, a conic of type 2, 3, or 4, is tangent to D? So let me just by way explain. By the way of language, we say that a complete conic CC star in phi is tangent to D. Well, that means exactly that CC star is in ZD. So this is our definition of what it means for a complete conic to be tangent. It just means it's the limit of smooth conics tangent to D. So that's our definition of tangency in this context. And so now we ask, if we have an arc in ZD, if we have a family of smooth conics tangent to D, if CT is a family of smooth conics, family of conics with CT smooth for T not equal to 0, and tangent to D at a point, say P sub T, again for T not equal to 0. So we have a family of conics, each of which is smooth conics, each of which is tangent to D, and we want to take the limit of those conics. That will be a limit in phi. That's going to be a conic of one of these, potentially one of these other types, 2, 3, and 4. And we ask, what does it mean to say that it's a limit of conics tangent to D? So let's say the limit of CT is of type 2. In other words, it's of the form L plus M comma 2P star. So that means, again, just to be concrete, we have a family of conics that are specializing to a pair of lines. What can I say about, if I know that the general member of that family is tangent to D, what can I say about the special member? Well, that's not hard to see, actually. If you have, so in other words, if C naught is a pair of lines, well, all we have to do is ask ourselves, where does the point P go? So the point is this: if the point PT if the limit as t goes to 0, let me put it this way. So that's the point of tangency. If that's not equal to p, so that's a point on L or M, but not the point of intersection, then the limit of the tangent lines is necessarily either L or M, depending on where P lies. And that says, so if limit of PT is not equal to P, then what that says is that either L or M is tangent to the curve P. And of course, if the limit of PT is equal to P, then it follows that P is in P.
What's PT?
PT is the point of tangency. See, we have these smooth curves CT, right? Which are specializing to a line pin. And each curve CT is, for T non-zero, is tangent to D at a point which we'll call PT.
Or maybe several points.
Pardon?
Or several points.
Or several points, but in order to take the closure, it's enough to take a general arc. So we can avoid the locus where there's an ambiguity about which point of tangency we need. Or we can make a base change. But the point is, if we have a family of these curves, and they're all tangent to some curve D, I look at where the point of tangency is going. If the point of tangency is going to a smooth point of C naught, then the tangent line at that smooth point, that would either be L or M, depending on which component P is lying in, the limit is lying in. That would necessarily be tangent to the D itself. On the other hand, if the point P of tangency approaches the singularity of C naught, well, then all I know is that point of singularity is a point of D. That's all I can say. But either way, the conclusion is that the set of complete conics, so let me write it this way, a complete conic, L plus M comma P, or 2P star, is in ZD if and only if one of these two conditions holds. L or M is tangent to D, or P is in D. And you can do a similar thing for the other two types, the remaining two types. I won't go through that. But look, that's enough to tell you. This is now an exercise, but it's one of these things that's worthwhile doing. I claim that based on this, I can now say that no conic of type 2, no complete conic of type 2 is tangent to all 5. So from this characterization, I'm going to just call this an exercise, what I can say is that if C1 up to C5 are general conics, then no complete conic of type 2 will satisfy these conditions for all 5. It will be tangent to all 5. It takes a page or so of argument if you really write it down carefully. The point is, if I have 5 conics, and I ask, can I find a line pair that satisfies this condition, or rather one of these 3 possible conditions, with respect to each of the 5, you can see pretty easily it's not. I mean, for example, if P, for one thing, since the conics are general, neither L nor M can be tangent to more than 2 of them. Okay? So that means P has to lie on at least one of the 5 conics. If it lies on 2, if it's one of the finitely many points of intersection of, say, C1 and C2, then you can check that neither L nor M can be tangent to more than one of the remaining conics. So again, you can't satisfy this condition with respect to 5, and the remaining case is that P lies on exactly one of the conics, and I'll leave that to you to work through. The point is, this characterization allows us to conclude what the crucial fact that when we take these cycles, Z or Z sub Ci, on the space of complete conics, we get, they intersect only at the points that we actually are interested in. So, again, the conclusion is, and now we're just about ready to start pulling out the calculation, for C1 up to C5 general, the ZC1 up to ZC5 intersect only in the locus of smooth conics. And finally, that means that we've eliminated the problem, and now we can say that the answer to the original problem, how many smooth conics are tangent to 5 given conics, is expressible as the intersection product of the classes of these hypersurfaces. So this is just the degree of the class of Z sub C to the 5th power in A5 of phi, which in fact is just Z. So now we've got the problem set up. And not too soon. It becomes now just a problem in intersection. Let me just run through. I don't want to, and I don't have time to go through the details of this calculation, but it's reasonable to see what you do in this case. And it also illustrates one further point that I've mentioned during this week, but I'll illustrate it again here. All right, so now we've just, remember we had this sort of paradigm for solving enumerator problems? The first step was find a parameter space. And then there were 3 more steps, right, which we haven't done here. The second was to describe the Chow ring of that parameter space. The third was to find the classes of the cycles we're intersecting. And the final step was to actually carry out the multiplication in the Chow ring. And we've only got the first step so far. So how do we find the Chow ring? The answer is we don't in this case. In fact, it is possible to give as an algorithmic description of the Chow ring of a blow-up. So we could, if we needed to, look this up, and we could write down the Chow ring of the blow-up. That's fairly advanced stuff, though, and I don't want to get into that. The point is that in some sense, to solve this problem, we don't need to know the entire Chow ring. We only need to know a subring of the Chow ring that includes the class we want to work with. So, in fact, in particular, in this case, since this is a divisor, this is a codimension 1 cycle, ZC, it's enough to know just the group of divisor classes. So the claim is that the Picard group, or let me write it in the way we're writing it these days, is A1 of phi is of rank 2 exactly, and it's generated by the classes of the pullbacks of hyperplanes, by the pullbacks of hyperplane classes from P5 and P5 star. Alpha and beta of the hyperplane classes, or hyperplane class in P5 and P5 star. So briefly, how do we see this? Well, that would follow from a general description of the Chow ring of a blow-up, but in fact it's not hard to see. Remember, we started phi, right? We can write phi as the open subset of smooth conics union a pair of divisors. The divisor D1, maybe call it D sub 2, are the complete conics of type 2. D3 is the complete conics of type 3. And I mean here the closure of those loci. So these are divisors, closed subsets. And these are, and so we can write phi as this union. Now I claim, first of all, that A1 of U is torsion. U is an open subset of projector space, whose complement is a hypersurface in projector space. Any line bundle on U can extend to a line bundle on projector space, and it's, if not that line bundle, then its sixth power. It can be represented by a divisor supported on the complement of U. That means the sixth power of any divisor, or of any 6 times any divisor class on U is trivial. So A1 of U is torsion. That means in turn that any divisor on phi can be expressed as a linear combination of these two. So that's the statement about rank 2. Now, for many reasons, it's easier to work with this pair of generators rather than the classes of D2 and D3. And so you just have to check that these are independent classes. Okay? What you can do also, so now we want to write out not the full Chow ring, but just the fifth powers of these guys, or the monomials of degree 5 in these two generators. And I'll do that. I'll write them out, and then, again, depending on the time, I will justify them or not. Not, probably. Well, some of them are pretty obvious, like, for example, alpha to the fifth. Well, look, this is just, alpha is the class of conics through a point. It's a hyperplane in P5 pulled back. I'm asking, when I ask for alpha to the fifth, I'm asking how many conics are there through 5 points? 5 general points in the plane. And you guys know that. There's 1. Alpha to the fourth beta, well, here we're asking, if I look at conics through 4 points, that's a general pencil of conics, how many are tangent to a line? And if you think about that, you look at the linear system cut on the line by those conics. That's a degree 2 pencil, and by Riemann-Hurwitz, it has 2 branch points. And similarly, you get alpha cubed beta squared is 4. And now the rest come by symmetry. Alpha squared beta cubed is 4 again. Alpha beta to the fourth is 2, and beta to the fifth is 1. Again, we're asking here, a priori, how many conics are tangent to 5 lines, but that's just the same thing as saying how many of the dual conics pass through 5 points. The last step is to express the class of ZD. Let's call that zeta, as a linear combination of alpha and beta. And that, again, you do by the method that we've introduced and used by now several times of undetermined coefficients. We write zeta as a linear combination with unknown coefficients. And then we intersect with curves in phi to get linear relations on those coefficients. We find at the end that zeta is 2 alpha plus 2 beta. It's a good exercise. There's a lot of good exercises here. Curious, if you took D to be a curve other than a conic, a cubic, a smooth cubic or something, you could likewise compute the class of its class, or the class of the locus of complete conics tangent to it, and you can work out the answer to the analogous question of how many conics, for example, are tangent to each of 5 cubics. But we barely have time to finish the calculation here, so let's just do that. We're just about done now. In fact, the class zeta to the fifth, well, zeta is just 2 alpha plus 2 beta, so this is 2 to the fifth times alpha plus beta to the fifth, which is 32, times alpha to the fifth is 1. Then we have 5 alpha to the fourth beta, so that's 5 times 2, that's 10. Then we have 10 alpha squared beta cubed, alpha cubed beta squared, I apologize. That's 10 times 4, or 40. And the remaining terms, again, are just symmetric with the first 3. So that's 32 times 102, or 3,264. That is the correct answer to the question of how many conics are tangent to 5 conics. And this is true. I mean, I have 1 minute. No, I don't. I'll stop there. To the space of complete quadrants. You can look at we can compactify the space of quadrant hypersurfaces in Pn in a way analogous to this. But you cannot do this, for example, for the space of cubics. If I asked you how many cubics are tangent to 9 conics, in fact, you would have to, I think in that case, blow up 5 times, and it would be a huge mess. Paolo Alufi did this when he was a graduate student, and I think it was the most miserable year of his life. So I don't recommend it.
What were you going to say if you had 2 more minutes?
Now let's see. Just, yeah, I sort of by way of an apology and also an exhortation. You know, all this week, in the interest of getting to sort of see how you actually use these ideas, I've been consistently ignoring a lot of foundational aspects, both in the foundations of intersection theory and also the sort of verifications that you need to make sense of this. I mean, just to take this last example, we're intersecting 5 hypersurfaces in the space phi. How do I know they meet transversely? I've shown by passing from the original P5 to this new parameter space phi that I've eliminated the problem of an obvious excess intersection. The intersection takes place entirely within the locus of smooth conics, but how do I know it's transverse? Maybe these solutions occur with some multiplicity. If I want to know that there are exactly that many conics, I have to check transversality. And throughout this week, I've been ignoring those things. But I want to say that you learn a lot from doing those. It's worth going through these things and filling in the details, dotting the I's and crossing the T's, as we say. And that's and you learn a lot of basic. In fact, all this material, in my experience, is a wonderful way to learn algebraic geometry, not just intersection theory, because going through these steps forces you, or helps you, depending on your point of view, to learn, you know, a lot of the foundational aspects of algebraic geometry. Yeah.
So the previous number was 7,776.
Yeah, that's right.
So, but in some sense, the intersection was infinite set of points.
That's right. The intersection.
But you did produce a number. I mean, you didn't produce infinite. You produced a number. So, 2 things. Is there some geometric meaning to this difference?
Yes.
Or is there some homological machinery, some first homology group, and then you have such like Euler characteristic which produces the...
No, the answer to both questions is yes, absolutely. And this is the content of Fulton's excess intersection formula. What Fulton's excess intersection formula is in a situation like this, in the original P5, so this is in P5, we had the intersection of the ZCI consisted of the actual solutions, smooth conics tangent to all 5, union the locus of double lines. What Fulton's intersection formula does is it assigns a number to this component, even though it has the wrong dimension, it assigns a class, in fact, of the right dimension, of dimension 0 to S. And then such that the sum is 7,776. And so the number that Fulton's formula gives you for that component of the intersection is exactly the difference. When you subtract it, you get the right answer.
I mean, this geometric setting, is there a meaning to this class?
Yes. This is the excess intersection formula is a formula involving essentially normal bundles of these loci. And you can actually see where it comes from, though not from reading Fulton's book. You can see where it comes from by thinking about what would happen if you did deform these cycles into cycles meeting transversely. So you can derive the formula yourself. This solution to the 5 conic problem is in Fulton. He actually explicitly shows you how to apply the excess intersection formula in this case and arrive at the number 3,264 by subtracting the contribution of S from 7,776. All right, I think we got a break here, so thanks again. Appreciate it.